The multiplication rule for independent events. Welcome, everyone. Before we dive into today's new topic, let's take a moment to recap what we've already covered. In our previous lesson, we explored the conceptual and formal definitions of independence, specifically looking at how we use conditional probability to understand how events relate to one another. We established a very important fundamental principle, that two events are considered independent if the occurrence of one event has absolutely no effect on the probability of the other event occurring. In other words, the outcome of the first event doesn't change the likelihood of the second. Building on that foundation, today we are going to move from theory to application. We are going to derive a powerful mathematical tool known as the multiplication rule. This rule is incredibly useful because it does two things. First, it allows us to precisely calculate the probability of both events happening at the same time, and second, it provides us with a mathematical way to test and prove whether any two given events are truly independent or not. Let's get started. Derivation of the rule. Now that we have established the conceptual definition of independence, remembering that independence means one event's occurrence doesn't change the likelihood of another, we need a mathematical way to actually calculate these probabilities. To do that, we can't jump straight to the shortcut just yet. Instead, we must first look at the foundation, the general multiplication rule. This rule is more universal because it applies to any two events, E and F, regardless of whether they are dependent or independent. The formula is written as the probability of E intersection F equals the probability of E, multiplied by the probability of F given E. Let's break down what these symbols actually mean in plain English. When we write the probability of E intersection F, we are talking about the probability that both event E and event F occur together. Now, the second part of the formula, the probability of F given E, is what we call conditional probability. This represents the likelihood of event F happening, specifically under the condition that event E has already taken place. Keep this general formula in mind, because in the next slide, you'll see how this formula simplifies beautifully when we apply the concept of independence. The transition to independence. Now that we have established the general multiplication rule in the previous slide, let's see what happens when we apply the specific condition of independence. If we assume that events E and F are independent, we can refer back to our definition of independence. Remember, independence means that the occurrence of one event has no impact on the probability of the other. In mathematical terms, this means that the conditional probability of F occurring, given that E has already occurred, is exactly the same as the probability of F occurring on its own. We write this as P of F given E equals P of F. Now let's perform a simple substitution. If we take our general formula from the last slide, which was P of E intersection F equals P of E times P of F given E, and we replace that conditional part, P of F given E, with just P of F, we arrive at our main goal, the multiplication rule for independent events. This is written as P of E intersection F equals P of E times P of F. Essentially, this formula provides us with a much simpler way to work. It tells us that when events are independent, calculating the probability of both happening together is as straightforward as finding the product of their individual probabilities. In the next slide, I will show you how we can actually use this exact equality as a mathematical test to prove whether two events are independent or not. Using the rule as a test for independence. Now, I want you to pay close attention to this next point, because this is where the math becomes a diagnostic tool. Up until now, we've been using the rule to find a probability, but the multiplication rule is actually our primary mathematical criterion used to determine if two events are independent in the first place. So, if you are presented with two events, let's call them event E and event F, and you aren't sure if they affect one another, you can follow this specific testing procedure. First, you need to calculate the individual probabilities, which we write as the probability of E and the probability of F. Second, you take those two individual results and calculate their product. That is, E multiplied by F. Third, you must determine the actual, observed probability of the intersection, which is the probability of E intersection F, meaning the probability that both happen together. Finally, you simply compare your results. If the probability of E intersection F is exactly equal to the probability of E multiplied by the probability of F, then you have mathematical proof that the events are independent. However, if the probability of E intersection F does not equal the product of E and F, then the events are dependent. We are going to see exactly how this works in practice in the next slide, with a real-world example involving a coin and a die. Real-world example. Now that we have understood the theory and how to use the rule as a test, let's put everything we've learned into practice with a real-world example. Imagine a scenario where you are performing two actions at the same time. You toss a fair coin, and simultaneously, you roll a fair six-sided die. Our goal here is to calculate the probability of a specific joint outcome, getting a head on the coin and rolling a 4 on the die. To solve this systematically, let's follow 3 clear steps. Step 1, we need to define our events. Let's assign the letter E to represent the event where the coin shows head, and let's use the letter F to represent the event where the die shows a 4. Step 2, we need to find the individual probabilities for each event. For the coin, the probability of event E, which is the probability of getting a head, is 1/2. For the die, the probability of event F, which is the probability of rolling a 4, is 1/6. Step 3, this is where we apply the multiplication rule we discussed in the previous slides. First, we must ask ourselves, are these events independent? Since the result of the coin toss has absolutely no influence on the outcome of the die roll, we can confirm these events are indeed independent. Because they are independent, we can use our simplified formula. We state that the probability of E intersection F, which just means the probability of both E and F happening, is equal to the probability of E multiplied by the probability of F. When we plug in our numbers, we get the probability of E intersection F equals 1/2 multiplied by 1/6. When you multiply these fractions, you get 1/12. So to conclude, the final probability of both getting a head and rolling a 4 occurring together is exactly 1/12. Now, before we wrap up, let's look at some common pitfalls to avoid so you don't lose marks on exam questions. Common mistakes to avoid. Now, before we wrap up our lesson with the final summary, I want to pause and discuss some common pitfalls. Even students who understand the concept of independence can lose marks by falling into these 3 specific traps. First, watch out for confusing addition with multiplication. It is a very common error to add the probabilities, such as the probability of event E plus the probability of event F, instead of multiplying them. A helpful tip to keep in mind is to look at the wording of the problem. When you see the word and, which refers to the intersection, denoted by the symbol U-shape, it usually implies you should multiply. On the other hand, when you see the word or, which refers to the union, denoted by the U-shape, that is when you involve addition. Second, be careful about assuming independence. It is tempting to jump straight to the multiplication formula we derived earlier, but you must never assume events are independent without verification. Always check if the problem explicitly states that the events are independent, or better yet, use the product formula to prove it before you proceed with calculating the probability of E intersection F. Finally, this is perhaps the most important point. Do not confuse independence with mutual exclusivity. These are 2 very different concepts. If you see the probability of E intersection F equals 0, that means the events are mutually exclusive. However, for independent events, the probability of E intersection F must equal the probability of E multiplied by the probability of F. In fact, if 2 events have non-zero probabilities and are mutually exclusive, they actually cannot be independent. This is because if they are mutually exclusive, the occurrence of one event completely prevents the other from happening, which definitely changes the probability of the second event. Keep these distinctions clear in your mind as we move to our final slide for the key takeaways. Key takeaways. All right, we have reached the end of our lesson. Let's take a moment to recap the key takeaways from today's session to ensure everything is clear before you move on to your practice problems. First, let's revisit the core formula. Remember, when we are dealing with independent events, which we've labeled as event E and event F, the joint probability, meaning the probability of both happening together, is calculated as the probability of E intersected with F, which equals the probability of E multiplied by the probability of F. It is also important to remember the origin of this rule. As we discussed earlier in the derivation, this isn't just a random formula. It is actually a simplified version of the general multiplication rule. In the general rule, we have the probability of E intersected with F equals the probability of E multiplied by the conditional probability of F given E. However, because we have established that for independent events, the conditional probability of F given E is simply equal to the probability of F, the formula becomes much more straightforward. Next, keep in mind that this rule serves as our primary mathematical test. If you are ever unsure whether two events are truly independent, you can use this equality as a proof. If you calculate the product of the individual probabilities and it exactly equals the probability of their intersection, you have mathematical proof that the events are independent. If they don't match, they are dependent. Finally, think about the practical application. This rule is an essential tool in your mathematical toolkit. It is the go-to method whenever you need to calculate the probability of multiple, unrelated outcomes occurring simultaneously. That concludes our lesson on the multiplication rule for independent events. Great job following along today.